This lesson is about graphing trigonometric functions. Let's recall transformations of graphs. In order to obtain a new function g from the known function f, just by adding number d outside of the function, we need to translate the graph of the original function f by a vector 0d. That means if d is positive, we are moving it d steps up. So adding a constant outside of the function causes vertical translation of the graph. Horizontal translation can be obtained by adding some constant by the x inside the function. So to obtain a new function g from f of x plus c, what we need to do is to translate the original function f by the vector negative c0. So if c is positive, the translation goes to the left. If c is negative, it goes to the right, opposite direction. Let's graph new function sin x plus 1 by transforming function of sine. So let's recall how sine looks like. We start with 0, go up to 1 at pi half, then towards 0, then negative 1, and then 0 again. So that's a curve of sine. And now in order to graph g of x, which is sin x plus 1, we shift every single point one step up. So all these points will be moved one step up. And the curve is the same. We will usually graph just first period of the curve, unless stated otherwise. So that's good enough. We know that this wave will proceed farther both ways. Okay, so the green shape is g of x, and the yellow is our original sine f of x. Let's do the same in example b. Starting with cosine, we're going to graph cosine of x minus pi quarter. Okay, cosine starts from 1, goes towards 0 at pi half, then towards negative 1, 0, and 1 again. That's the full period. Let's join the points. Somehow like this. And then to create the graph of function g, what we need to do is translate the original graph of cosine by the vector pi quarter 0. So pi quarter to the right, because we're subtracting pi quarter, so we need to move everything pi quarter to the right. Therefore, this point goes here, that one over there, this one here, this one there, that one there. And join all the points like this. Okay, so the red one is the graph of function g, and as before, the yellow one is the basic function cosine. So here we have example of vertical and horizontal translation. We can make a general observation. If we want to translate original graph of trig function vertically by a vector 0d, that corresponds to a vertical shift of the midline. The midline for the original function is the line y equals 0, which means x-axis. So this midline was moved, in this case, one step up to the new position. So the new midline has equation y equals d. If we add a constant d outside of the function, that means that our previous midline will pass through the point d on the y-axis. If we analyze horizontal translation though, then the translation by a vector c0 corresponds to something that is called phase shift by a constant c. So in our case, c was actually pi quarter. So the phase shift takes opposite sign to the number that you see in the bracket. And this phase shift in this example was visible here. We moved the original graph by pi quarter to the right. All the points pi quarter to the right. So if we combine all what we learned already about graphing trigonometric functions, we've been talking about amplitude, that's the absolute value of the coefficient before the function. we've been talking about b being responsible for the period. And now we covered the vertical shift and also horizontal shift. So a constant d outside of the whole function will be responsible for the vertical shift and also a horizontal shift. And also we've been talking about horizontal shift, but in this case, if the function is written in the form as you see here, then we actually don't see the x plus or minus some constant. Then we actually can't tell how much the x is shifted because there is some b in front of it. We would have to change this form in order to see the horizontal shift. But this c together with the b will be responsible for the horizontal shift. As long as we take in consideration the coefficient b. So we'll see it in a second how to change this form so it will be easy to read the horizontal shift. For now, this horizontal shift is not quite there yet. Okay, so let's list some steps how to graph a trig function in that form. First, we keep in mind the basic shape, the name of the function, together with the sign of the coefficient a, gives us the information about the basic shape. For example, basic shape of sine would have a curve like this, but the basic shape of negative sine would go the other way around. So it's good to keep this in mind. The next step would be to see the phase shift. That means to rewrite this function in a form that we can actually see what the x was shifted by. So what we do, we pull the b outside as a common factor, and we would like to have in a bracket just single x plus or minus some constant. So if it's x plus c over b, because if we took the b out, then we have to divide by b here. And therefore the negative c over b will be our horizontal shift. Well, the term phase shift or horizontal shift, that really means the same. So you can use those terms interchangeably. Okay, so far we know the basic shape of the function. We can read the phase shift here, which is negative c over b. That means the constant that we see in a bracket by the x with opposite sign. And then we want to start graphing boundaries for the first period of our future function. So those boundaries will be as follows. It will be a vertical line, x equals negative c over b, that's the phase shift. So that will be the left-hand side of our future full period, and the right-hand side will be bounded by this phase shift plus the period. As you remember, the period is easy to calculate just by taking the regular period of the function, if that was sine or cosine, it will be 2 pi, and divide by the coefficient b. So if we know the period, we add to the phase shift, we have the right-hand side boundary. Okay, so we know that our full period of the function f will have to fit within these lines. And then we draw horizontal lines. Those horizontal lines will start with the midline. The midline is determined by the coefficient d. So the midline is somewhere, let's say here, and then what we do, we add to d the amplitude, either positive or negative. So if a is known, we know that this many steps we can go up or down. So that's a general strategy. Now we know that the full period of our function should fit within this rectangle. And in the following step, we should subdivide the midline segment, this segment, into 4 equal sections. So cut it in half and then cut it in half again. So 4 equal sections, those will be your future quadrants. Finally, we need to plot the key values of the basic trigonometric function, which was stated here, within this basic rectangle. And after we have them, join to get the shape of the function. So, for example, for regular sine, I would have to mark this point, that one, and that one, and then join it. So that's the way of graphing any trig function. Well, let's practice it then. In preparation for developing this rectangle that will help us to graph the given function, we would like to state the shape, amplitude, period, midline, and the phase shift. Then we are going to sketch this rectangle for the full period, marking the key values, join them, and that's how we obtain the graph. Okay, but the first thing is to rewrite this formula in a form that will show us the phase shift. That means take the 2 as a common factor outside of the bracket. So our f of x could be written as -1/2 sine, and then take the 2 outside, second bracket, x plus pi over 4. Because 2 times pi quarter is pi half. So that would agree. -3. Okay, so the shape is of negative sine x. The amplitude is 1/2. The period, well, let's calculate this on the side. P equals sine has regular period 2 pi, divide by 2, so it's pi. The period is pi. The midline is this -3. And the phase shift is the opposite sign to the number that you see in a bracket. So it's -pi quarter. Okay, so let's try to graph it. We start with the phase shift, -pi quarter. So if this is -pi quarter is here. Draw a vertical line. The period is pi, so go pi steps to the right and draw another line. Now let's draw the midline at -3. So -3 is here. And we can go by the amplitude. The amplitude is just 1/2. So 1/2 will be here from the midline up and from the midline down. So this is our rectangle that the full period is supposed to fit. And now we're ready to graph. We basically have all information that are needed and follow the shape of negative sign, which is like that. So we start with the midline, that's like a 0. So we need to subdivide this segment into 4 sections. Those will be our quadrants. And then plot the key points. Starting from the midline, we can pretend that's our 0. Then we go towards -1, 0, 1, and 0 again. So in this new kind of system of coordinates, in respect to the midline, that's how the graph will look like. And obviously, if we have the first period, we can easily proceed to draw some more of this function. But the main part is to graph the first period. The rest is really easy. We already know how to proceed. Go slam that. And so on both ways. Beautiful. So that's our function f of x. Well, let's go to the second example. In order to read all information about this function, it's a good idea to rewrite it in the form that will show us the shift. That means factor -pi out. So this is 2 cosine -pi, and then it's x minus, and then it's 1/2 plus 1. But notice that cosine of negative is the same as cosine of positive because cosine is even. So this whole thing can be written as 2 cos of just pi times x minus 1/2 plus 1. Now we're ready to read the information about the function in order to graph it. So the shape is of a regular cosine. The amplitude is 2. The period is 2 pi divided by pi, so it's 2. Period is 2. Midline, well, that's 1. Phase shift, opposite to whatever we see in the bracket, so it's 1/2. Great, let's start drawing. we start drawing from the phase shift, 1/2. This is 1, so this will be 1/2. Vertical line through 1/2. And then we draw another vertical line full period ahead, like 2 steps ahead. So there will be 1, 2, it will be somewhere there at the point 2.5. Good, now horizontal lines, starting with midline, which is at 1. Go by the amplitude, 2 up and 2 down. So 2 up is here, 2 down is there. So this way we created a full rectangle which will contain the first period of our function. So in order to draw this function, again, let's divide this full segment, midline segment, into 4 equal sections and follow the shape of cosine, which starts from the top, goes towards 0, bottom 0, and the top. So the top 0, bottom 0, top, and join smoothly those points. So the shape will look like this. Okay, that's our function f of x here. So if you practice this on many examples, it shouldn't be any problem. This is a really easy way of graphing. So follow these directions, please. We have 2 more examples, one with tangent, the other with cosecant. As before, let's change the form of the function first so we can see the shift. 1/2 tangent. We're taking 5/2 as a common factor out of x minus. And how to get this number? Well, the pi is here, since 5 will have to be reduced, so the 5 goes down and the 2 goes up. You can always check by multiplying if you've done it correctly. So yes, 5 is reduced, 2 is reduced, we end up with pi, so that's good. Plus 3/4. Shape of the regular tangent. So as you see, the basic functions we need to have in our minds. Amplitude is 1/2. Period, the regular period for tangent is pi, and then we divide by 5/2. So it's the same as multiplying by reciprocal. So that's our period, 2 pi over 5. Midline is 3/4. Phase shift is 2 pi over 5 as well. And we'll start graphing it. So as before, start with the phase shift, 2 pi over 5. If I have the segment pi, if I divide this into 5 equal subsegments, then 2 of them, that means this point, will be exactly 2 pi fifth. Fantastic. So this is the center. It works like y-axis before for the tangent. So the tangent will be spread in both ways from the central line. How far? Since the period is 2 pi fifth, then we go 1/5 pi to the right and the other 5th pi to the left. Therefore, this point is 3 pi fifth and that point is just pi fifth. Okay, there is one more thing. We have midline at 3/4. Since this is 1, the 3/4 will be half away here on this square. The 3/4 will be half away between half and 1, so exactly here. So now in order to graph the shape of tangent, we pretend that these 2 lines are like new system of coordinates. So now we are nearly ready to graph the tangent, except that we still need to accommodate for this kind of amplitude, because for tangent, for the point that is half away between the center and the asymptote, normally we would have a value 1, but this time it will be multiplied by 1/2. So the graph is a little bit more flat around the center. And the same is here. Instead of -1, from the midline it will be -1/2. So that's the point. Therefore, the graph will go close to the asymptotes and then pretty flat around the center and then pretty steep towards the asymptote. So that's just because of this amplitude 1/2. If it will be 2, then it will be stretched, will be steeper around the center. Okay, and the last example is about cosecant. So again, let's rewrite this function to see the phase shift by taking 2 out of the bracket. So that will be pi quarter, because pi quarter times 2 is pi half. And then we are ready to list the information about the function. Shape is of negative cosecant. Amplitude 3/2. Period, well, cosecant has regular period 2 pi divided by 2, so it's just pi. Period is pi. Midline is exactly at -1. Phase shift is at negative pi quarter. Okay, let's start with the phase shift. Negative pi quarter, that will work like our previous y-axis for the regular shape of cosecant. So negative pi quarter, here it's this line. The period is pi. That means if I open it towards the right pi, the full period should fit within these 2 lines. Let's quickly recall how cosecant looks like. Since cosecant is reciprocal of sine and sine goes like that, then cosecant will go like this. Since we are talking about negative cosecant, then we'll expect the shape to be like that. So let's use the midline. Midline is at -1, which is somewhere there. So this will pretend like the previous x-axis, and that will be like the previous y-axis. Now, halfway between the endpoints of the period is another asymptote for cosecant, like here. And the 2 branches will be positioned somehow like this. One in the bottom, here, the other in the top. But we need to also accommodate for the amplitude. The amplitude is 3/2, which means that from the midline we go 3/2. This is 1.5. Okay, so another horizontal line will be here and 3/2 over there. Now we are ready to graph the shape. So the shape follows these asymptotes here, and starting from that point, it will follow those asymptotes. Here we go. Obviously, this situation repeats itself for more periods, but that's good enough for us. Okay, so we know how to graph a function given a formula. Now we see a graph of certain trig function. We need to recover the formula. So let's see the first one. Well, it would be nice to determine where's the full period and what is it that we really want to take, because it's not only one unique formula. You can give couple formulas that will describe exactly the same shape. So if I take, for example, this part of the graph as a full period, then I could think about negative cosine and build the formula around negative cosine. So if that's f of x, my f of x could be negative cosine. I leave the room for the amplitude. And then I need to know the phase shift and the period and the baseline. So let's put this information together. First of all, amplitude, it's really easy to recognize. That looks like a midline. So the amplitude is from here to there. That's 1.25, which is 5 quarters. So we have -5 quarters for sure, cosine of something. This cosine starts from -1/4. So inside the x, I should have +1/4, because -1/4 is my phase shift. I still need to figure out what is the b coefficient, and the midline is pretty easy, so it's +1 outside of the function. So what's this coefficient? Well, let's look at the period. From here to there, it looks like it is exactly 2. So if the period is 2, the b is the same as the regular period of cosine, which is 2 pi divided by 2, so it's really pi. Okay, so this number must be pi. And that's the complete formula for this function. Obviously, you could come up with the formula that will refer to sine rather than cosine. For example, if you take this section of the function, that will be sine. Well, let's see. How else can we express this function? Let's try to use sine. Again, the period is the same as 2. Therefore, the b coefficient is pi. So we have sine of pi, and the shift is positive 1/4, so we'll have to have x minus 1/4. The midline is also 1. No change here. The amplitude is still the same, 5/4, but there's a positive sign. So either like this or like that would work. And you're welcome to plug it in both formulas to the calculator and see that they really produce the same graph. Okay, let's see the second graph. If I choose the section from here to just about here, so this will be the one full period of some function. Well, what is this function? That looks like it's connected with cosecant, but it's upside down, so it's negative cosecant. We still need to figure out what's the amplitude here, but it's negative something cosecant. Now, how to figure out period? Well, it looks like it's just pi, because this segment is the same as that segment, so if you shift it, it will be pi. So if the period is pi, the b coefficient is actually 2 pi over pi, which is 2. So we have cosecant of 2 times something. Now we need to figure out what is this number. That will be the shift. Since this is pi thirds, and that's 1/3 of the way, so it must be negative pi ninths. So we're subtracting negative, therefore we're actually adding pi ninths. And the midline looks like it's here. This point is negative 1/2. So we subtract 1/2 outside of the function. Now we still need to look at the amplitude. The amplitude is this distance, and that distance is 1/2 as well. So we write negative 1/2 cosecant 2 of x plus pi ninths, that's the input, minus 1/2 outside. So that's our f of x. Final answer. Okay, let's look at the following examples. You may want to try to discover those formulas by yourself before I do it on the video. So please stop video and see if you can do it on your own. Let's take one full period that looks somehow like here, the asymptote. The other asymptote, it's most likely here. We can only estimate sometimes because the scale doesn't always show every single aspect, but we need to try our best. So from here to there, it looks like the period is pi half. So since period is pi half and the regular period of tangent curve is pi divided by pi half, the b coefficient looks like it's 2. Okay, let's see where's the midline. The midline looks like it's going through number 1. So that's 1. Okay, and the shape looks like it's increasing like a tangent. So the f of x could be written as tangent, possibly with some coefficient, but we'll see it in a second. B coefficient is 2 times. Is there any shift? Well, the center looks like it's coming through the point. If this is pi half, and there's 5 sections here, so this point will be pi tenths, 1/5 of pi half. So we'll have x minus pi tenths, because the phase shift is pi tenths, so it's minus. Okay, that's the input. Now the midline is 1, so it's plus 1 outside for sure. And what's our amplitude? If we look at half away, then what is the value? Well, the value looks like it's 1/2. So 1/2 tangent of 2x minus pi tenths plus 1. So that will be our function f of x. And again, try to plug it into the calculator, see if that makes sense. Finally, the last graph. Oh, that curve looks like it has something to do with cotangent because it's decreasing like that. Obviously, we could use negative tangent as well and shift it, but let's try cotangent this time. So that's f of x. Our period is 2 pi, so the b coefficient is pi over 2 pi, which means it's just 1/2. The midline comes through, if this is 5, that must be 1. And the phase shift is pi quarter. This number is pi quarter. So I think we're ready to give the formula f of x is cotangent of 1/2 x minus pi quarter, possibly with some coefficient here, we will check on that in a second, plus 1. Now what is the amplitude? If we look at half away, what is this value? If this is 1, that's 2, therefore this must be 1/2. So it's 1/2 cotangent of 1/2 x minus pi quarter, and outside plus 1. Final answer. So I hope you had enough of examples. Now you need to start practicing on your own. And a couple more interesting examples. We need to graph f of x, which is a sum of cosine x and also just x. So we have a graph of cosine in green, we have a graph of y equals x in orange, and in blue we'll try to add them point by point. So 0 plus 1 is still 1. We'll just look at the critical points, like 0 plus this point, it will be the same point, so this point doesn't change. Then this point is -1, so we need to drop this value by 1, so our value for the sum function will be here. And we need to connect those points. Okay, let's try a couple more. If we add 0, we don't change anything here. If we add 1, this point will be raised by 1, somewhere there. And 0, the same point, and -1 over here. Maybe one more, 0 is here. Notice we'll have to go through all these points nice and smoothly. So basically what's happening is the cosine is winded around the x. It goes somehow like this. Similar pattern, but it's not periodic because the values actually change. So that's how you add two functions. One more example, 2 to the x exponential function. That's 2 to the x, the orange one. And this one is -2 to the x. And the green one is sine. Now if we multiply them, remember we had similar examples before? This 2 to the x actually works like an amplitude, but changing amplitude. So the wave of sine will move up and down the same as before, so the zeros will be kept at the same places. However, the amplitude will change. So instead of 1, I have very tiny bit here and over there, but this one is already more than 1. That one is here. That one will jump there. And now we need to connect those points. So the graph will look somehow like this. And this is lower, higher, and a lot lower, and so on and so forth. So oscillates between these two curves, 2 to the x and -2 to the x. Find an equation of a cotangent function with period pi/2 and phase shift -pi/4. This time we don't have the graph, but we have some information about the future function. So let's call it f of x. Cotangent function, so I need to use cotangent. Period is pi/2, therefore my b coefficient is pi divided by pi half, which is 2. So I need to multiply the input by 2. And the phase shift is negative pi quarter, so I add, because it's minus negative pi quarter, so I add pi quarter inside the bracket, and that's my function. So that's one of such equation. Obviously, you can multiply this cotangent by anything you wish. You can add or subtract anything you wish. It will still satisfy these two conditions, and that's all what we care about. And finally, we have one application problem. During a summer day, the ground temperature at a desert location was recorded and graphed as a function of time. And here is the graph. T is the number of hours from 6 a.m. So this is the horizontal axis. Time since 6 a.m. Therefore, this point corresponds to 6 a.m. And that point, with the number 3 here, it really corresponds to 9 a.m. and so on. This temperature is most likely in Fahrenheit, but the question didn't state that. The graph can be approximated by that function. So something about cosine, where t is the number of hours since 6 a.m. Find the equation of the graph and approximate the temperature at 1 p.m. Well, we have just a form of equation of the graph. We don't have specifics. We really need to find out A, B, C, and D. What's the easiest? Probably D. That's the midline. That's the position of the midline, which looks like it's at 90. Because this is 80, that's 100, that's 120, so half away will be 90. Therefore, I know that my future f of t is equal cosine bracket plus 90. Now amplitude, the A. If I use the function of cosine, and let's say if I want to start with this bottom from here to there as a full period, then the cosine is actually upside down, so I have to have a minus here. And the amplitude, this number is 60 and that number is 90, therefore the amplitude must be 30. So it's negative 30 cosine. Okay, and now it's important to find out the period. Obviously the period is 24 hours. That's the full day. Therefore the B coefficient will be 2 pi divided by 24. So it's pi 12. Okay, so we use pi 12 here, but then we have to use another bracket and accommodate for the shift. The shift is negative, so here it will be plus. And the shift is by 3 hours, so it's plus 3. Here we go. That's the formula. Now, second part of this question calls for approximating the temperature at 1 p.m. Well, first of all, we need to locate 1 p.m. If this is 6 a.m., then adding 6 hours will be 12. So this point on the number line really corresponds to 12 p.m. Therefore, 1 p.m. is at 7. Okay, therefore we really need to calculate what f of 7 is. Negative 30 cosine pi 12. 7 plus 3 is 10, so times 10 plus 90. And now we could use a calculator, or we could actually try to find out the exact value, because 10/12 is like 5/6. So we really have negative 30 cosine of 5 pi 6. And we know how to deal with such angles. Those are special angles, right? So 5 pi 6, let's recall, that's a little bit less than full pi by pi 6. Therefore, the reference angle is pi 6. Okay, so this is the same as negative 30 cosine of pi 6, but our angle is in second quadrant, so cosine of 5 pi 6 is the same as negative cosine of pi 6, and then plus 90. Now using our special triangles, This angle is pi 6. So cosine of it is root 3 over 2. So we really have negative is plus 30 times root 3 over 2 plus 90, which is 90 plus 15 root 3. So that's exact number. I've done it just because I wanted you to recall how to deal with special angles, but you're welcome to plug it in the original expression to the calculator and approximate the value. So this is approximately 116 degrees, most likely in Fahrenheit.